Welcome to The Explainer. Today, we're going to pull back the curtain on the fundamental language of all modern electronics. I mean, everything from your phone to your car speaks in a language of electrical pulses. So we're going to break down exactly what that language is and, more importantly, how it works.
So here's the game plan for this explainer. We'll start with the absolute basics. What are data and signals? Then we'll look at the two big types, and from there, we'll build our way all the way up to the very heartbeat of every digital system, the clock.
All right, let's dive right in. The first thing we need to wrap our heads around is how a simple piece of information, like a letter in an email, even begins its journey inside a device. At the very bottom of it all, you have these two key concepts, data and signals. Think of it like this. Data is the what. It's the actual message, the raw info you want to send. But that information can't just float through the air. It needs a messenger. And that's where the signal comes in. The signal is the how. It's the physical voltage that actually carries that information from point A to point B.
Okay, so we know what a signal is, but it turns out these little messengers come in two fundamentally different forms. And honestly, they operate in completely different worlds.
On one side, you've got analog. It's smooth, it's continuous, and it can have an infinite number of values, kind of like a dimmer switch for a light. But on the other side, you've got digital. Digital is discrete. It only has two states, on or off, high or low. We call them 1 and 0. There's nothing in between. So if analog is a smooth ramp, digital is a set of stairs. You're either on one step or the next, period.
And this picture just illustrates that perfectly. On the left, you see that smooth, flowing analog wave. Think of a sound wave. And on the right, you've got that sharp, blocky digital signal. Every time it's high, that's a 1. Every time it's low, that's a 0. It's super direct, totally unambiguous. So why is pretty much everything in our world digital now? Well, it all boils down to one word, reliability. Because a digital signal is only ever a 1 or a 0, it's incredibly tough. A little bit of electrical noise or interference isn't going to accidentally flip a 1 to a 0. This makes it super robust, easy to check for errors, and it means you can copy data a million times without it ever degrading. That right there is the foundation of the modern world.
So if our entire digital universe is built on these ones and zeros, let's zoom way in and look at the most basic building block of a digital signal, a single pulse.
So check this out. This is what we call a positive pulse. It's really just a quick jump up. The voltage starts low, shoots up to a high level for just a moment, and then drops right back down. That initial jump, the part that goes from low to high, that's the rising edge.
And, you guessed it, here's the opposite, a negative pulse. It starts out high, takes a quick dip down to a low state, and then pops right back up. In this case, that leading edge is the transition from high to low, and we call that a falling edge.
Okay, so these diagrams we've been looking at are super clean, right? Perfect right angles, instantaneous jumps. But let's be real. Is that what's actually happening millions of times a second inside your computer?
Not quite. See, in the real world, physics has something to say about it. It actually takes a tiny amount of time for that voltage to rise and fall. And signals aren't perfectly clean. They might overshoot the target a little, or even ring like a bell as they settle down. And to deal with these real-world imperfections, engineers get super precise. They measure things like rise time, fall time, and the pulse width. Why? Because they have to make absolutely sure that even with these little flaws, the system can still tell the difference between a 1 and a 0, reliably and at incredible speeds.
Okay, so we've got these individual pulses. Now, how in the world are they strung together to create something meaningful, like a word or a number?
Well, they're combined into what we call a digital waveform. And really, it's just a train of these pulses, a sequence of high and low states. The code itself is stunningly simple, but so powerful. High voltage means 1, low voltage means 0. That's it. That is the entire language.
Now, these streams of pulses, they tend to come in two main flavors. Some are periodic, meaning they have a pattern that just repeats itself over and over at a fixed interval. Others are non-periodic. Their timing is unpredictable and random, which is what you'd see when real, actual data is being sent. For those repeating periodic waves, we can measure their frequency. Frequency, which we measure in hertz, tells us the speed of the signal. It's literally the number of times that pattern repeats every single second. And yep, this is exactly what you're hearing about when you see processor speeds measured in gigahertz.
But hold on. With all these ones and zeros flying by, sometimes billions of times per second, how does a system know exactly when to look at the signal? I mean, if it looks at the wrong nanosecond, it could get the entire message wrong.
The answer is the clock. The clock is a special, perfectly periodic signal that acts like a metronome for the entire digital system. It doesn't carry any data. Its only job is to provide a steady, rhythmic pulse that every single component in the system listens to.
Okay, look closely at this slide because this is where it all clicks. That top waveform, that's the clock, just ticking away, perfectly regular. The bottom one is the actual data. Now, the system is designed to only look at that data signal at a very specific moment, like right on the clock's rising edge. At that exact instant, it asks one question. Is the data high or is it low? A 1 or a 0?
So, and this is the crucial takeaway. The clock is like the conductor of a digital orchestra. It's not playing an instrument itself, but it is making sure every other part of the circuit plays its note at the exact right time. It keeps the entire system in perfect harmony.
And just like that, we've gone from this abstract idea of data to a physical reality, a precisely timed electrical language of ones and zeros that honestly forms the foundation of all modern computing. But that leaves us with a huge question, right? This binary language is incredibly simple, just 2 characters. How does that simple on-off code build our entire complex digital world of text and images and all the apps we use every day? Well, that bridge between our human world and the computer's binary world is built with something called number systems. And that is exactly what we are going to explore in our next explainer. Thanks for watching.